Courses in the cement industry. Present to you. In this course, we will discuss ovality analysis for rotary kilns and other refractory-lined rotary units. Can be defined. Ovality analysis. Ovality is a measurement of how well a rotary kiln shell is able to support refractory. Rotary kiln refractory brick linings depend on the principle of the continuous arch to stay in place. Naturally, any forces acting on that arch, such as a flexing rotary kiln shell, will act to deteriorate the mechanical stability of that arch. It is not uncommon, therefore, for refractory to literally fall out in a short time after installation if excessive flexing of the rotary kiln shell exists. Also can be defined. Rotary kiln shell ovality. Definition. The change of curvature of the shell plate is caused by normal rotation. Note: if the rotary kiln is not turning, it has no ovality. Ovality is a change of curvature during rotation. So if the rotary kiln does not turn, the curvature cannot change. It is important to realize that ovality is a dynamic measurement, and should not be confused with shell deformations, such as wrinkles, or flat spots, or permanent damage caused by refractory failures. The principle of distortion measurement. See in this figure. Distorted cross-section. To determine delta H it equals A minus B. To determine ovality it equals. Brief about the principle of distortion measurement. The principle of ovality measurement was established by a patent in 1952, by Carby. It is a measurement that was developed to monitor the behavior of the shell as it directly affects refractory. The steel shell is very flexible when compared to refractory brick. The flexing, as far as the shell is concerned, is usually no particular problem. That is, it normally will not cause the steel plate of the shell to crack. But there are defined limits to shell flexing, which should not be exceeded, if the refractory is expected to survive. Ovality measurement tells us the mechanical stability of refractory. We follow together. Ovality measurement. Ovality measurement is a measurement of the mechanical stability of the refractory. All rotary kiln operators need to know the behavior of their rotary kiln under its various conditions. Routinely making ovality measurements provides a history of conditions, which can be used to analyze refractory problems. This can be easily done by plant personnel, using any devices to measure ovality. Ovality determines refractory stability. In this figure, it is the rotary kiln tire that determines the ovality of the rotary kiln shell. Thickness of the tire determines bending strength. Face width of the tire determines Hertz pressure. We follow together. Ovality determines refractory stability. Ovality is not just an arbitrary consequence of rotating the rotary kiln. It is actually a design parameter. The production requirement of the rotary kiln dictates its size, specifically its diameter, length, slope, and speed. This information is then given to the mechanical engineer, who then calculates the weight of the rotary kiln, and from that determines the number of required supports, their locations, shell plate thickness, tire dimensions, roller sizes, etc. When sizing the tire, the maximum allowable bending stress largely determines its thickness. The maximum allowable Hertz pressure large dictates the face width. Although this would completely define the tire. This gives us a measure of how much the tire will flex. Since the refractory will require the flex to also be kept to an allowable maximum, either the tire thickness and or its face width may have to be increased to satisfy this requirement. It is, after all, the tire that controls the shape of the shell. We follow together. Ovality determines refractory stability. In this figure, the tire dictates the basic shell ovality. But where the shell is not supported by the tire, ovality increases by the size of the gap. We follow together. Ovality determines refractory stability. The tire controls the shape of the shell. However, it can only do so where the shell is in intimate contact with the tire. For most rotary kilns, the bore of the tire is somewhat larger than the shell. This is because there needs to be room for the shell to expand, since the tire expansion will never be quite as much. This difference in size manifests itself at the top of the rotary kiln. Because the shell is so much thinner than the tire, it does not remain a true cylinder but will fill the tire, leaving a flat spot across the top. As a consequence, the shell will flex more than the tire as it travels through this flattened area across the top. The shell ovality is therefore always somewhat larger than the tire ovality. Only when the shell is unexpectedly overheated to the point where it expands to completely eliminate this gap, will the shell ovality be the same as the tire ovality. Gap, ovality, and temperature difference between the tire and shell, differential temperature, are all related. When the tire and the shell are at the same temperature, shutdown condition, the gap is maximum, the ovality is maximum, and the temperature differential is zero. During a rapid heat up, the shell will get hot fast, the tire will still be relatively cool, and the gap could disappear. A gap is zero, ovality is minimum, equal to the tire ovality, and the temperature differential is maximum. Because the tire bore and the shell will wear over the years, this gap will increase in size. This could become dangerous for the refractory because of the increased ovality that results. These figures illustrate the normal ovality curve. Interpreting ovality curves. The ovality curve would be a straight line if the rotary kiln tire and the shell were perfectly stiff and did not flex during rotation. This would be the case if the tire were a solid disc, for example. For most rotary kilns, the greatest amount of flexing occurs at the supports, directly at the tires. Since the shell is much thinner than the tire, it has far greater flexibility, so its shape will usually conform to the tire. The shell is much like a bag of water, which would take the shape of a bucket when placed into one. This is true as long as the tire and shell are close size to size. We know in the case of floating tires that there is a difference in size, the shell being marginally smaller than the bore of the tire. This is a simple mechanism to accommodate differential thermal expansion between the tire and the shell. We follow together. Interpreting ovality curves. This difference in diameter manifests itself predominantly at the top of the rotary kiln and is called the gap. Since the tire and shell are not keyed in these designs, the tire actually migrates around the shell over a period of time. This movement is commonly called creep. In the area of the gap, which is at the top, the shell assumes a flatter position than the tire. As the tire passes over the rollers, it also tends to straighten out. The entire weight of the rotary kill shell, and its contents acts to push down, causing the sides of the tire to push out slightly. These variations of curvature are seen in the illustration above. These phenomena are present in every rotary kill, only their magnitude will vary. To protect the refractory, these movements must be kept to a minimum. Interpretation of ovality curves. Common characteristics. In these figures illustrate heavily loaded, or undersized tire. In these figures illustrate excessive tire and shell gap. In these figures illustrate bowed shell, requires at least 2 curves. In these figures illustrate underloaded pier or oversized tire. In these figures illustrate misalignment, pier holding shell, left in relation to adjacent piers. In these figures illustrate cracked shell plate. We follow together interpretation of ovality curves. There are a variety of common variations to the typical curve that is frequently displayed by some rotary kilns. Using the electronic ovality beam, these signatures are easy to see. With a little practice, a great deal of additional information about the behavior of the rotary kill shell can be deduced beyond just establishing the ovality measurements themselves. The more typical signatures are shown in the illustration on the previous slide. In the following slides, actual examples from our files are shown. Typical shell characteristics. Data taken from actual readings. See in this diagram. Abrupt change of curvature indicates a shell crack. Excessive shell gap. Interpreting ovality curves. In the previous slide, the sharp point in the curve means the rotary kill shell is cracked in the axial direction at the location directly under the ovality tester. The break in the curve results from a hinge, like the action of the shell plate along the crack as it turns. This curve is taken from an actual rotary kill measurement, and it was somewhat coincidental that the instrument was placed straddling the crack. Often such cracks are not obviously visible. But in the event such an ovality signature appears, it should immediately be cause for closer investigation. Indication, differential shell slope. See in this diagram. Downhill curves. Uphill curves. Kill shell top center. In the previous slide. Indication, differential shell slope. It is normal practice to take 6 sets of readings at each tire, 3 around the circumference spaced at 120 degree downhill of the tire and similarly 3 on the uphill side. One would expect that the curves would all be very similar in shape. In this sample, however, the 3 downhill curves are distinctly flatter than the 2 uphill curves. This is particularly noticeable at the rotary kill top dead center, highlighted in the illustration above. This set of curves shows there is a larger gap on the uphill side of the tire compared to the downhill side of the tire. This is possibly caused by the shell not running at right angles to the tire. This condition will exist when the mid-span sag of the shell towards the feed end does not match the mid-span sag towards the discharge end. We simply define it as a differential shell slope. This condition has been observed to cause severe wear, in a short period of time, of the side wall of the tire, and on the stop blocks in contact with it. There are many different shell conditions that this instrument can highlight. Some extreme shell characteristics. See in this diagram. Instrument slipped. Typical misalignment signatures. Heat expansion of the beam. Some extreme shell characteristics. In this example, we have taken readings for 2 consecutive rotations of the shell. This has been done to highlight the effects of severe temperature change on the instrument. The instrument in cold conditions was placed on a very hot rotary kill shell. The effects of expansion on the instrument can be seen from the graphed raw data. The readings should be the same after 1 revolution. This would require the line labeled heat expansion of beam be parallel to the 0 line. It is not necessary or recommended that the ovality beam be left on the shell for acclimation before the readings are taken. The 2 small dips in the center of the graph are the roller signatures. One would expect these to be equal, indicating that the shell is sitting centered on them. Since one roller causes a greater shell deflection than does the other, this shows that the shell is sitting off-center, closer to the roller with the lower dip on the ovality curve. If this characteristic is reflected in all the curves for a tire, and a similar pattern is mirrored on adjacent pairs, this would be a clear indication of roller misalignment. If this pattern alternates from one curve to another, it would be an indication of a bent shell. Any abrupt jogs in the curve are clear indications that the instrument has moved while taking readings. This happens frequently if the magnets do not seat properly when the instrument is applied to the shell. As the instrument then travels to the top point of rotation, its own weight may cause the magnets to draw flush with the shell, causing a jump in the curve as shown above. Ovality measurements. See in this diagram. Damaged shell plate causing erratic and unpredictable curves. Ovality measurements. In the previous slide, ovality is affected by many factors. Every rotary kiln has an inherent ovality dictated by its design. Principally, it is the thickness and width of the tire that determines the ovality at each support. In addition to that, influences such as shell fit, gap, shell temperature, shell deformations, rotary kiln loading, and alignment can have significant contributions to ovality. For that reason, it is sometimes difficult to say which factors may be dominant. As can be seen from this example, ovality curves can deviate significantly from the expected pattern when one of these factors becomes significant. For this reason, all the available tools, visual inspection, alignment measurements, and shell profiling, creep measurement and temperature measurement, are needed to completely understand the mechanical operation of the rotary kiln. Case study. 1. Kiln specifications. Kiln problems. 1. Mechanical instability. 2. Unsatisfactory refractory life. Recommendations. 1. Ovality analysis. 2. Alignment. 3. Replace ring support pads, filler bars. 4. Recondition rings, and adjust rollers. We follow together the analysis of Case Study 1. A typical rotary kiln was selected to highlight a very common problem. High shell ovality due to high clearance between the shell and the tire. This problem is usually associated with refractory instability. In many cases the problem can be rectified without replacing the shell section under the tire. If the excessive clearance between the tire and the shell gap is solely due to an enlarged tire bore, and worn tire support pads, filler bars, chairs etc., then a successful repair, without cutting the shell is possible. Careful inspection for shell deformation under the tire is required. If shell deformation is not a contributing factor to an excessive gap, support pad replacement is a more economical solution, and should be considered thoroughly. Many rotary kilns have been successfully restored in this manner. We follow together the analysis of Case Study 1. See this diagram. Ovality curve, and findings from hot alignment, before repairs. We follow together the analysis of Case Study 1. In the previous slide, this shows the initial raw data curve, indicating a high ovality. A high creep was measured at the same time. These two indicators, when observed consistently, are a sign of high shell-to-tire clearance. The small negative dips, the roller signatures, are not equal, an indication of roller misalignment. It should be understood that only one curve is shown here for clarity. A full history of curves is necessary, since ovality can vary widely with rotary kiln conditions. With a history of curves, typical rotary kiln conditions can be identified, and decisions based on these average conditions can then be made. This one curve, therefore, has been selected to show that average condition. We follow together the analysis of Case Study 1. In this figure, alignment before roller adjustments. We follow together the analysis of Case Study 1. In the previous slide, the alignment diagrams show some misalignment which was properly identified by the ovality measurements. If no other factors strongly influence ovality, and misalignment is significant enough, the ovality curves usually reflect the condition of alignment, as in this case. We follow together the analysis of Case Study 1. In this figure, acceptable ovality range. We follow together the analysis of Case Study 1. In the previous slide, the acceptable ovality for any rotary kiln is approximated by taking its diameter expressed in meters, dividing it by 10, and expressing the result as a %. For example, a rotary kiln of 3.4 meters in diameter has an expected ovality range that should be centered on 0.34%. In this case, 0.61% was measured, a figure clearly high of normal. Acceptable ovality is an empirical derivation simply based on years of observations. In this figure we see the cross-section of the rotary kiln. We follow together the analysis of the cross-section of the rotary kiln. In the previous slide, this diagram was drawn using ovality measurements to calculate the radii of the rotary kiln shell. The difference in the length of the radii was amplified to make the shape of the shell visually obvious. This then, with its multiplied scale, is how that shell actually looks during rotation. We clearly see two areas of compression, one at each side of the shell, and one area of relaxation at the top. Every brick undergoes these three cycles, with each rotation of the rotary kiln. A rotary kiln turning 2 revolutions per minute produces almost 9,000 cycles per day, for each brick. It is easy to see therefore, that significant stress is put on the refractory, when this movement becomes excessive. In this video, compression and relaxation cycles per turn. 1. In this point, shell pinches, bricks compress. 2. In this point, shell flattens, and bricks loosen. 3. In this point, shell pinches, bricks compress. In this video, compression and relaxation cycles per turn. 1. In this point, shell flattens, and bricks loosen. 2. In this point, shell pinches, bricks compress. To calculate cycles per day, we use this equation. In this figure, zoom in on refractory. Before repairs, we note the following. Here we have a close-up of the top area, under a relaxation cycle. The principal cause for this high measured ovality, was that the clearance between the tire and the shell, was much greater than it should be. In this figure, zoom in on refractory. After repairs, we note the following. The clearance between the tire and the shell, less than before repairs. Case Study 1. This chart. Raw data curve. After repairs, we note the following. Shown are the ovality measurements after repairs and after roller adjustments. We can see a clear reduction in span of the raw data. We following with us. Raw data curve. This chart. Before repairs. Note. Improvement on roller alignment, after adjustments. His chart. After repairs. This chart shows acceptable ovality range. Note. The calculated ovality from the new data shows that it was reduced to 0.43%. This is not as low as it probably was when the rotary kiln was first manufactured, but it is a significant improvement which will provide many years of improved refractory performance. Ovality and brick wearing speed. There are further indications that keeping ovality under control has an impact on the life of a rotary kiln. In 1995, Yoshiki Dujiya, Iliki Nakajima, and Toru Honda of Mino Yagio, Ceramic, Co. conducted a study of the interrelationship between refractory life and rotary kiln shell deformation. In their paper, presented at Uniter 95, they considered the mechanical stresses caused by ovalities. The effects of chemical or thermal stresses were not considered. The authors gathered data on the measured ovalities and brick life and analyzed this data statistically to find the interrelation between them. In figures 1 and 2 above, the interrelation between the measured ovality data and brick life is shown. The linear regression line is calculated by the least squares method. Figure 1, brick life decreases with the increase of ovality. Figure 2, it was found that there is no correlation of brick life with ovality for tire 1, discharge end. In the burning zone of a rotary kiln, the bricks are exposed to severe thermal load conditions and corrode quickly. Bricks in this zone are usually protected by the material coating. When this coating becomes unstable and falls, it spalls the bricks. Therefore brick life varies, and no interrelationship was observed. Interrelation between ovality and brick life. in the previous slide. Figure 3. This better demonstrates the interrelation between ovality and brick life than Figure 2. Although minimum brick life figures were used, the brick life at the number 1 tire was above the linear regression line. This means that large ovality accelerates the wearing speed of burning zone bricks. Conclusions. When ovalities increase in the center zone, between tires, not only are bricks stressed from the shell, but lined brick rings slip from the shell. Brick life is further reduced in the center zone. An acceptable ovality limit for a certain period of rotary kiln operation was discussed, according to the calculations obtained. The authors confirmed that maintaining tire ovality within the acceptable range has a positive effect on brick life. Further studies are being conducted. Original article was printed in World Cement, April 1996 and is used by permission. Routine ovality measurements. 1. Understand shell behavior. 2. Maximize refractory life. It is only with routine ovality measurement that the behavior of the shell can be fully understood, and refractory life can be maximized. Remember, it is always necessary to take shell, tire temperatures, and creep measurements whenever ovality measurements are made. There is a strong relationship between these three which should be documented for all kiln conditions. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.